Hello everyone, welcome to GIS Man. I'm Miles Lee. In this video, I'm going to share how to program the neural network with Pytorch to help the spatial data analysis. So the neural network is currently one of the most popular and welcomed machine learning methods in many AI applications. The terms that we heard very often, the deep learning, is actually using the neural network as its backbone technology. So let's get started. So now let's take a look at our app map first. So right here we have several feature classes. In the AADT training dataset, we have the information about the road traffic volumes. This is coming from the sensor that we install on each road segments. It can record how many cars go by each road segments per year. So what you can see right here, the colorful road segments got such detectors, and it can record how many traffic volumes it has for a year. And then at the same time, we also have the information like the drive time, which indicates that how long does it take for the drivers to go through each road segment. And we also have the functional type, which indicates how do we use the road. For example, if this is the high road or this is just a low quality community road. And we also have the GNF point count. This information is coming from the Australian Statistics Bureau. Is the point feature classes, and each point represents the address for the houses or building nearby the road segments. So the traffic volume are highly correlated to these three informations. So what we are going to do is to build up our neural network, and based on this training model, based on this training data set, we need to train our neural network model to find out the correlation, and then use the trained data model to predict some road segments, as what you can see, the non-colorful one. As what you can see in the testing data set, we still have the drive time, functional type, and GNF point count, but the AADT derived, which is the traffic volume, is empty. So we need to base on this to predict the final results. And this only happened after we trained our neural network. So let's go back to our notebook to see how it can be implemented. So there are in total 6 steps to implement the whole process. In this video, I will firstly implement the first 3 steps, and then in next video, I will continue to talk about the rest. The first thing what we need to do is to read in our training data set. I have already turned the feature classes into the CSV. And then I also put this CSV to my Jupyter folder. And at the same time, of course, we will need some libraries, for example, like the NumPy, which is used for the array management, and PyPlot, which is used for displaying the training process, and then the Torch function, the Torch neural network, which is used for constructing our neural network and also train our data. The Pandas, which is the mathematical tools, which is used to construct and manage our data frame. And scikit-learn is a library that can be used for normalization. I will talk about the normalization later, but you don't really need to worry about that at the moment. So first thing is to read in our training data set. Let's do that. Right here is pretty easy. We just need to use our Panda Library to read in the CSV. Gnef to train.csv, and then we also need to indicate which column is the index column, because later when we turn it into our NumPy, we don't want our index columns to be involved, because index column is not meaningful at all for our training. Okay, so and then after this we can turn this Panda data frame into our NumPy array. So we can print it out to take a look. Firstly, we print our original Panda data frame, and then we print our NumPy array. Let's run. So what you can see, this is the Panda data frame. It contains 3 fields and 1 label. And then we also got the transform NumPy array. What you can see is a 2-dimensional array and has 4 columns in each array. Okay, it's pretty easy for this step. And then the key is coming. We will need to build our neural network. This is the neural network diagram. And by the way, I strongly recommend you guys to use this tool. This is the open source tool to draw the diagram before you designing the neural network, because it can help you to make clear about your logic, your requirements, and how you could implement in your coding. Okay, so it's very convenient. You can change how many neurons, how many hidden layers, and what's the output neuron look like just by changing the number. And you can design your neural networks right here. And then later on, you can according to this diagram to implement your code. So let's do that. So what we can see here is we have 3 arrays of columns as our input, which is our functional type column, Gnef total column, and drive type column. And we also have an array of columns as our output, which is our AADT derived label. And then in between, we will also have several hidden layers with multiple neurons. So we will need to write a class to represent and illustrate the structure of this neural network. So let's do that. So we will need to define a class. I call it the neural net. And then the parameters, we will need to transform our Pytorch module. And then we will need to define 2 functions. One is our initial function, and the other one is our forward function. I will talk about them step by step. Okay, so firstly, in our initial function, we will need to inherit our Pytorch neural net characteristics. So we need to call the superclass. Okay, and then we will need to define our hidden layer. Use the Pytorch.neural-network.linear to illustrate the structure of the neurons in the hidden layer. So right here we have 3 array of columns. So here is 3, and then we have the 120 neurons for the first hidden layer. So here is 120, okay. And then for the second hidden layer, they are of the same structure. So it's right here. For example, previously we have 120 neuron, and then the second hidden layer we have also have 120 neuron. Okay, so here we write it as 120 and 120. So this is important. The first hidden layer is from our input to the first. So the definition is the input array of columns to numbers of neurons in the first hidden layer. And then the second hidden layer, or the deeper hidden layers, the third one, the fourth one, or the fifth one, they are of the same structures, which are 120 neurons in the previous hidden layer to 120 neurons in the current hidden layer. So here is 120 to 20, 120, okay. And then the output layer, based on the same rule, we will have 120 neurons for the previous hidden layer to our output, which is an array of the column. Okay, so here is 120 to 1. So now you can see the interesting thing is based on the diagram, we can easily to illustrate the neural network by our programming coding. Okay, input is 3, the first layer 120, and then the deeper hidden layer, for example, the second hidden layer, the third hidden layer, the fourth hidden layers, they are all of 120 to 120, 120 to 120. So here is the 120, and then the output layers will be the 120 neurons to one array of column. Okay, so that's 120 to 1. For the deeper hidden layer, we can write as many as we want. That can be implemented in our forward functions. Okay, so let's go to our forward function. A forward function, on one hand, it defines the structure of our neural network, and on the other hand, is also used to calculate the value for each neuron at the same time. So the input value, we assume that the value coming from the previous neuron, the input value is x, and then going through the first hidden layer, and then generate the first temporary output, and then this output need to go through what we call the activation function. There are lots of activation function can be choose. For example, here I use the red loop, but some people, they will also use a sigmoid function, and it depends. Red loop is good for regression cases, for example, like the linear regression, polynomial regression, or sparse data regression. As what I draw the diagram right here, this is the linear regression. This is the polynomial regression. We can see that the x has some polynomial factors on top, and this is a sparse data regression. I mean, red loop function is very good for the regression cases, and sigmoid, some people they are use it for classification cases, like for example in the image detection or image tracking, video tracking cases. I mean, the sigmoid function is quite frequently used. Okay, so here we take the input and go through the activation function on each neuron to generate the real output for the next layer. Okay, and then after that, we can even write a loop to extend our neural network to be deeper. For example, here we have 3 hidden layers, so I just loop through the hidden layer 2 for 3 times. Of course, I mean, if you want the network to be deeper, you can write this to be 5 or to be 6. So in this case, you know, there are more layers in our neural network. But in this case, you also need to think of your time complexity, because the larger neural network it is, the more time it takes to train your data model. Okay, so currently I just, according to my pre-designed diagram, I make the deeper hidden layer as 3. And then also it needs to go through the ReactJS activation function. Okay. And finally, here we will define the predict. The predict y, what it means is for our array of columns for our output. Output layer, it takes our previous input and then to generate the output. So this is the structure of our neural network. You see, it's not that difficult. Actually, the deep learning is not just, you know, highlight the rocket we can't reach. It's very easy to implement with just less than maybe 20 lines of Python code. Okay, so finally we will need to return the result. So this is our structure of the neural network. Let's see, there are some errors right here. Oh, TouchNN has not attribute module. I typed it wrong, so that will be fine. So that's fine, yeah. So now we have already construct the structure of our neural network. The next step is to normalize our input data. Because what you can see, the input data right here, the value is quite big. For example, some of them are 112, some of them are even higher. This one is 1,300, something like that. We will need to make all of them range from 0 to 1. The reason to do this is to help our neural network to converge easily. Otherwise, I mean, in our neural network, there is a phenomenon called the gradient explosion. If the training data's value is too high, the neural network cannot be converged to our desired direction, and then the gradient will be explode, which results in we get nothing. The trained model is failed to predict our final results. Okay, so that's why we need to do the normalization. So this step is also easy. We can use our previously introduced scikit-learn library to implement this. So the first thing what we need to do is to use a class called min-max scalar. Min-max scalar. This is a class in scikit-learn library. Okay. So with this, we can use an embed function called fit transform, and then pass our previously defined the NumPy array, and then it will generate a normalized version of NumPy array. Okay, and then we can print it out and take a look. So what we can see right here is the values in our original NumPy array have been transformed to the values between 0 to 1, no matter how big it is. Okay, so after this, we can start to split our data. We need to split the first 3 columns into one set as our input, and then split the last column as another set as our output. Okay, so the input, we call it X dataset, which is equals to our normalized NumPy array for all records, all rows from the column index 0 to index 2. Actually, this is 0, 1, 2, okay? And then our Y dataset, which is our output, will be from our NumPy array normalization version for all rows to the last column. Okay, so here is column 3 as our output and column 1, 0, 1, 2 as our input. So we can print it out to see the results as data and Y data. And we just run it. So what you can see now, the data has been split. But what we don't want is the Y data. It shouldn't be like this. We don't want it to be dumped in an array in a flat type. We want it to be a column type, because later on when we train the data in the neural network, it takes the tensors, and the tensor need the array to be the column type instead of the row type. Okay, so we will need to do a little bit transformation about this. We will need to reshape it for all row NP and M, and then we need to reshape it into just a column type. You can run it again. So now you can see the difference. The Y dataset, the output dataset, has been transformed into the column type array. So this data can be used for later neural network training. So in next video, I will show you how to adjust the neural network parameters, how to set up the log functions, optimizers, and how to build up the tensors. Then how to train the dataset and predict the results with our trained neural network model. So if you like this topic, please stay tuned, and I will see you next time. Bye.